So, hello everyone, welcome back. And before we actually start diving into this engaging and extremely immersive and extremely enjoyable experience, I just want to clarify that why am I making this video? See, this is not for your generic JE types or the trash way physics are taught in schools and coachings, um, which absolutely embark no interest in students, uh, and they of course then they hate physics and they are unable to approach it, and they feel fear that how can we approach it, and even after choosing science field they have terrible fear and terrible experience with physics especially, apart from maths. So it's a attempt. This video series will be an attempt to clarify all of it. And see, it is not. I am not standardizedly focused on this JE and all this. This is for your own understanding that how actually physics came from. So of course, this all these equations of motions and all those, they did not come from the sky. Neither did calculus and neither did differentiation integration. These did not come from the sky. Especially Newton and Laplace. They did not Leibniz. They did not derive it for fun. Like I mean, they some god did not come to them and they just said that okay, today we are in the mood, so let's derive this integration. So what they did was that they observed each and everything fundamentally, and they broke it down to each and every part that okay, this should be done. This is the reason, and mathematically this should be done, right? So of course, needless to say, mathematics came much before physics. So we exactly my attempt is to do that. It's like to tell how exactly physics is interconnected with maths, and how exactly physics came into existence. So and you will find it very interesting, I'm promising. And also one slight thing is that I will keep the language of this course in English rather than Hindi, because see, English is a very universal language. It is more what can I say, more explainable, more easy to explain to people, and it's more easy to reach other people also. So of course I hope that people outside India, and even people who are from the south, if they have any problems in Hindi, they can easily adapt to this course. So without wasting any time, let's just get started. I'm just too excited, right? So let's start from the very basic, right? So this example my maths teacher gave me, right? So I will also share that same example with you. So, all these physics and maths which you currently study, they were not, let's say, 5,000 years ago. Let's say 5,000 years ago, do you think there was any person who, studied integration as such? I mean, in generally that, okay, he came and he was admitted into a school, and in school in class 9th, he would learn that V equal to U plus 80. Basically, the equations of motion. Will he be like that? Of course, no. Right? Because during that time, it was not known at all. It was again upon the human individuals to discover it. Right? So let's start with the very fundamental thing, that how exactly this physics came into existence. Now, again, this might sound a bit philosophical, but everything starts with a bit of philosophy, especially. So, you are born, let's say, any human individual, let's say you are born, let's say some 5,000, 10,000 years ago, some born you are. Of course, not that much old, but I'm basically telling around 5,000, 4,000 years ago, 4,000, 5,000 years ago, you were born, right? So and you are wondering, and you are just born right now, let's say this is you, your little baby, and you of course slowly grow up and all those. So and of course alongside you many others are born. How are you born? That is again a subject of biology and genetics, which we have to look further on, but currently we are discussing physics, so let's stay limited to that. So this is you, and along with you some other babies also, somehow they came into existence, right? So now as you grew up, you became adults, right? So well grown adults with hairs and all, of course both genders. Again, please ignore my this kind of drawings. My drawing is really poor, but just get the understanding. Okay, so these are humans, so, right? So now from the beginning only, from your childhood, what are the things that you want, right? You want food for survival. See, these are the basic things which a human needs to survive. At least the human thinks he needs to survive. Food, basically. This is basically the animalistic nature, that okay, food, sleep, and reproduction. basically food you want, water, let's say another, food includes in water, but let's say you want, basically you want all these natural resources to survive. So initially 5,000 years back, let's say it was all a forest, I know it was very densely forested area. So let's say you were born in some kind of a jungle, and in this jungle there were many trees, right? So thousands of trees, and you did not have to worry much because fruits were already in the trees. So, and let's say this was a river, right? So let's say you and your few other couple friends, they grew up and they also had their own babies, and they lived here in this area, only restricted to this area. That's all they know about. So you ate food, you took water, and led a pretty life. Now let's say after a few generations, of course it cannot, the population is increasing very much. Now of course it cannot sustain this small region, this small area cannot sustain so many people. Let's say 1,000 people. Can 1,000 people be accommodated in this small area? And of course water would also be insufficient, or rather the food supply will also be insufficient. So people need more, right? So they have to survive. So what they do is now they start exploring, right? So this is where it comes from. So they start exploring, and from here, an idea which is very common, a very unique idea, is that whenever you are stuck limited into a small space, expand your scope, expand your perspective, so that you can understand more, you can gain more, right? So we'll talk about it more later. But let's say now, taking this example, this human, now he wants to, of course he needs all this food and all this to survive. So what does is that he sees that a few miles, let's say few kilometers, let's say 1 kilometer away, there is, he can see there is another forested region. Let's say here is some barren land, and here is another forested region, and again that region also has trees, the same streams, river, and it also has foods and all those. So uh, half of the population, let's say 1,000 people, so 500 people, they say that okay, we you stay here, as the space is less, so rest 500 will move on to here, and on and on and on. And of course, as you can understand, how this is again a very mathematical perspective, that how further things develop. Now if I go too much deep into that, I would have to shift into mathematics, because see, 500 people went to that. Now again, this region will also be limited. Then what will happen next? They will keep on expanding until they are occupy the entire forest. So basically what has happened now, every place on earth, they almost is occupied, right? So that's the thing, that's exactly how it began. So now as space is there, area is there, so now people, they, of course they, now let's say they want to convey with each other, so now they have to go back and forth each and every time. And let's say a person from here says that our there is a shortage of apples, so bring a few apples for the peoples, so that the shortage is minimized. So now let's say a person from this person goes to here, and he has to bring apples for that many people. Now of course he does not know that how many people are there, and there are so many apples here. So how can he bring all, and how many do he have to bring? So with that came the fundamental principle of counting. Not fundamental principle of counting. People mistake this with PNC. Please don't bother yourself with it. Just forget everything you know. Just start from the very basics, right? So he has to count that how many apples to bring and how many people are there. So correspondingly, let's say if one person requires two apples, so I have to bring. Let's say there are 5 persons, so 5 into 2 equal to 10. Now, of course, this is a much more deeper. They did not talk in 5 into 2 equal to 10. This decimal system, this is basically decimal system. This was discovered much more later. They, do you know what they did? There was some kind of bone, so they used to etch markings on it, and they, okay, so this many markings, so according to corresponding to these many markings, I have to bring this many apples. So basically if you read the elementary number theory by David Burton, you can gain more knowledge on how exactly this number theory came into existence. But again, that will become truly mathematical. Now of course I want to include mathematics in this, but again it would be too large, then it would be like the perfect course, honestly. But currently I don't have that much facility or manpower to do that. um, But anyways, I hope you can understand that this was how the population began. So now, of course, few people they lived like normally, that okay, fine, have kids and move on. So that's how life works. Move on from one place to another, and of course, count and all this, fine. So now, of course, there were so many divisions. So many divisions were there. So that's how we people were divided into continents, countries, and Italian, and then other Greek, Greek civilization, Egyptian civilization. So that's how it all spread, right? Initially, it was like this, and of course, after that, it spread. Of course, in middle of a desert, suddenly someone cannot come, right? I hope you are clear about that. So of course it's spread like this, right? So now, few people they wanted to question the very belief system, that how exactly is life working? How exactly did we come into this place? How, what is the significance of this life at all? I mean, few people they, of course, after years of seeing this, it felt very repetitive, and they might have thought that why exactly all this, that we are born, we move from one place to another, have kids, and maybe for further generations, and basically philosophy type. So that kind of people had a kind of, you can say, sanghatan, or rather kind of meet, a kind of group, that okay, we are philosophers. Of course they did not call themselves such, we call them philosophers, but you can read up, okay, you can, there are many philosophy books. A good one I forgot, it was Sophie's Diary, I think it was, the name I am forgetting. But that diary explains in much more detail that how exactly this philosophy emerged from. So anyways, so there were many philosophers, and and they basically wanted to question life itself, question life, and question these processes, that how is this flowing. This is, of course, can you understand this, this is just out of natural curiosity. They did not sat under a tree, which we normally hear, that okay, they did not have a book where they had to study, advanced physics, mathematics, and all those. They were actually not interested in, I mean, they were not forced to do it at all. They were just, for out of sake of curiosity. Now if I take some very high tech, you can say, or very good, very interesting thing, I keep it in front of you, then of course you will be very curious about it. You will try to open it, you will try to look through it. Basically we'll try various kind of things in order to know what it is. So similarly people also tried. So and there were many people, but now whom we are going to talk about especially is Aristotle, because previously he was one of the main. Now of course there are much more historical records now, of course. Many of them are not reliable, and they have gotten destroyed over time, but we have the a kind of more accurate historical record. So this is just another person who was belong to this category, that he always wondered about life and all those, basically the natural processes like rains and sun, how it arises and all those, right? So of course he did not talk about it in much detail. And see, when you will listen to his theory, you will just laugh at it, that okay, what does he actually mean? I mean, but during that time, can you realize it was just out of curiosity? It was not something that okay, some advanced mathematics or some advanced physics I have to develop. He did not do things because he wanted to be a physicist or something like that. He was just doing things out of sheer curiosity. So that's what made him famous, or you can say made him different. That's why we are accounting him. Now if I wanted to, as traditional teachings do, that I would have just started with equations of motions, that okay, children, write down v equal to u plus at. See, these are all kind of bullshit, right? So because actually no one came and told Aristotle that okay, v equal to u plus at, and no one came to Newton and told him that okay, I'm from the future, and in projectile, the equation of trajectory would be y equal to x tan theta minus g x square, that thing. Of course no one came and told Newton, right? So he found it out himself, and similarly we will also do it. So, the very birth of motion. So, this is a very deep historical, conceptual, and experimental construction, that you can say this was pre-Newtonian mechanics. You can kind of say, but again, uh, Aristotle did not know that Newton was to come. So basically, he was not much interested. Also, he was just interested to know more about life, that how exactly this all entire processes work. Like let's say this natural objects, river is flowing. How does it flow at all? So for that, he gave a framework, right? So he constructed his because we have a very you can say valuable information that okay, Aristotle was the one. He believed that the first listen to me, then you will I will write it down so that it becomes more clear to you. So he believed that all the objects possess an intrinsic nature and a purpose, like as humans do. Like okay, we have a destiny and all those. Again, there is a very philosophical concept, but destiny, we have a kind of purpose, right? uh, we are destined to come to earth, we have a kind of purpose, like it's kind of feeling that okay, we are the chosen one, we have been given a particular purpose and we have to fulfill it. So our, Aristotle, so what did Aristotle do? Aristotle said the same thing about objects. So see, now of course you might be wondering what purpose does a stone lying on the ground have. See, but again, this is just Aristotle's attempt to make things understand. This is not the actual, not mathematical. He was just, he did not, that's why we are not currently reading Aristotle, because Aristotle was, you can say, kind of very not mathematical, not understandable at all. It was morely based on faith. But let's see what he told. He told that each and every object, right? So all objects, let's say this pen, or let's say this mouse I'm holding, or anything, any this air or any stone which lies on the road. He believed that they possess an intrinsic nature, like they has something internal going on, right? And they have a purpose. So he called this, we name this thing as uh, teleology. But again, don't go to terminologies, they are just nothing, right? So he told that there are various objects. So now of course he sees that okay, there's a river, and the river carries this stones, and let's say here is a bank and it deposits these stones. So he gave the theory that okay, this stone's destiny, or rather this stone's intrinsic purpose was to flow with the river and get deposited as a bunch of sand and sediment, which people can use to cultivate soil, alluvial soil, basically you can say, basically cultivation purposes. So this was hard stone. So he believed that this stone had the purpose, internal purpose, that okay, I have to devote my life towards this, towards creating fertile soil. So he believed that okay, he came to the conclusion that okay, this rock, see, rock goes with the river, but let's say I have another tree, the tree does not go with the river. So that means motion is not random. He basically, I'm just telling you whatever he told, right? He observed that okay, see, trees are standing still. So why are they standing still? Maybe because they have food, and their purpose is to provide food to human, right? So stone is there. Maybe the stone's purpose is to again provide food to human, because fertile soil, alluvial soil, so that animals, organisms can thrive. So that's the thing. So Aristotle told that, concluded that okay, this motion, whatever motion we see, it's not random, right? It's not like okay, something happens on just chaos. It's not chaotic. Basically, he told that everything is goal oriented. Everything he believed that okay, this thing was fully, the stone's purpose. The stone moved at any. I mean, the stone moved even a little bit because it had to fulfill its purpose, basically to be the sand, or the tree grew up so that to fulfill the purpose, to feed the people. So that's what he believed. So he believed that this motion was not random at all, these were goal directed. So these objects, whatever, these trees or this water also, this stone, they move, or they undergo motion. Of course he did not use any term as motion, we coined this term much more later, but currently I am using motion so that it becomes more easier for you to understand. So this motion of the objects, the objects move because they want to fulfill their natural state, kind of what you learn in chemistry. Again, if you don't know chemistry, then forget it anyways, because we don't have any use. We will see it from fundamentally. But in case you know that, in chemistry we say that atoms, they lose electrons to attain the noble gas configuration, which is again very inaccurate, but still up to class 10th level what we are taught, we know that, or even class 6th 7th also it's taught, right? So that's the thing. Aristotle told kind of the same thing, that objects move to fulfill their natural state, like their purpose. So he classified this motion. Of course, now he was not from. Of course, he was not an English person. He was Greek. So of course he wrote all this in Greek language. Now of course I don't know Greek, So, and also I cannot present it here, so I'm going to write in English, of course. So if I translate in English, that he categorized motion into two parts: natural, right, natural and violent, right. So natural motion and violent motion. So that's how he categorized it, like, of course. So how did this categorization come? Again, from observation itself, that okay, all are flowing, so they are all flowing because they have a purpose, right. So natural motion occurred when, he told basically that when these objects move towards the natural position or the natural tendency, like let's say the stone's tendency is to what, to move with the river and become the sand. So basically, this flowing of stone is a natural motion, because it happens, by normal. I mean, it just happens for the sake of happening. It happens. And however, violent motion is such that okay, you pick up a stone and you place it on the top of a tree. So see, there it was not natural. Someone external came and took the stone and placed it on the top of the tree. So of course that is not natural. So he told that okay, this kind of motion, which is done by external forces or rather external influence, is, I'll call it violent motion. So that was just his categorization. He just saw that okay, either the stone will move on its own, or I can move the stone also. I can just take the stone and throw it, some far away, or I can just place it on the top of the tree or on the bottom of the tree, so, or inside the tree. I can do whatever I want. So of course was not natural, because this was not happening naturally. I did something, and as a result, that process took place. So that's why he named it as violent motion. And natural means what? Okay, the stone was here. After a few times, maybe floods will come and the stone will automatically go and become the sand, basically, after the decomposition. So that's it. So that was he mentioned. That what was he meant? That okay, this process is natural. So stones are falling downwards. Let's say from a hill, the stones fall downwards. So that is natural. But let's say I throw the stone purposefully into the river. So that is not natural. That is again violent. So he again observed that okay, fine. So he categorized this entire motion, whatever he saw, into two parts: either due to external influence, or by nature. And of course, now that he has made this theory, or he have given proposed this, that okay, everything happens because the object has some inner purpose, you can say intrinsic nature purpose. So what so of course he tried to apply it everywhere. He, previously, after fires were lit, let's say fire was discovered by then, by the time I'm talking about. So let's say he saw the fire, right. So he saw the fire, he saw the flames going upwards, right. So in flames they go upward, right, the gases and all. So he concluded that okay, maybe the fire is trying to reach something. Maybe there is something higher in there, and the fire is trying to reach something, and that is the purpose of the fire, to reach up, to reach somewhere up. So that was how he was telling, because of course now he has made this model. So now he was trying to apply it everywhere and to check that whether this is true or not. And he applied it in many places. He applied it in fire, this example of fire, and another very interesting example, or rather motion, which he applied this to, which I will come to. But now take for this example, he said that okay, this is natural process, because if I light up a fire, the fire will, the flames of the fire will be directed upwards. Now can you see, it's all very logical. Even you don't know that why does a fire point upwards. Now of course, if we go deep into science, we will know that again, pressure difference and all. But for Aristotle, this was a very, you can say, very big observation. First of all, he was mainly observing rather than, doing mathematical stuff, right. So he was observing that okay, this fire moved up, so maybe this fire has some higher purpose, or the fire has some intrinsic nature to move up. So basically, he was telling that okay, there was some relationship with the fire and the sky, so that's why, you can say, the fire moved. So that was what he told basically. And simultaneously with that, he also found out a very interesting thing, that basically what Newton later concluded, that okay, force and acceleration and mass, this all, he also found it out. What, of course, this was all coming out of his sheer observation. What he did is, he used to sit by a river bank, and let's say the river is flowing in this direction. So what he did is, he let's say he first what he did was that he took up a stone, of course, because he was just experimenting. He was just trying to apply this idea everywhere, that okay, if this works or not, right? So what he did was that there were two rivers, let's say one on this side and one on another side. So he came, he picked up a stone which was lying in this bed, and what he did is he threw it in water, right? And he saw this river was flowing with a greater speed, because it was, let's say, coming from a very high source. It was flowing with very high, you can say, speed, very fast, right? So he threw it there, and he saw that this same stone, this stone, you know covered a large distance in a very small time. So he kept one of his assistants here, that okay, stay here and count the time. By that time, counting and all those, by hourglass, that all came. So he threw the stone into the river, and he asked his companion to count the time. So he, of course, measured the distance also. So basically, how much time it takes to reach from this place to this place. So uh, he counted the time. So now he then asked his friend to collect the same stone, and after collecting it, they moved to another place, another river, right? So, and Aristotle again does the same thing. He throw again, same direction, the river flows in the same direction, but with a much slower speed. Like you can say it's very calm river, it's not very turbulent, so it's flowing with slower speed. So what Aristotle again does, here is Aristotle and here is his friend. So what he does is that he throws this stone inside again, right? And now he asks his friends to count how much time it has been. And now when his friends finds the stone and catches it, they again meet together, and then they see that okay, previously the time took was much shorter, and now of course it's, for us it's very obvious, but during that time it had to be tested out, because no one knew all this. So that's why Aristotle is very much, because he always questioned, right? So he was randomly experimenting. He told his, basically he was trying to apply his theory, that okay, let me see if I happen to throw this, what will happen. Of course it will flow. So he asked his friends to calculate how much duration is it taking to reach from his to his place. And he found out that the time taken here was much more lesser than the time taken here, because this is a slow river and this is a very fast river. Let me use a different color also. Yeah, this is a very fast river. So that's why the time taken to reach this, the same stone, it was nothing different. The same stone to reach from Aristotle to his friend was much more lesser in the former case. So he concluded, of course, again by observation, that okay, he was not mathematically writing, he was just concluding things. He just observed and he wrote down the observations. That is actually true science is. Mathematics and all, they of course come after observation. If observations don't happen, then uh, where will science come from? So he concluded that if the same object undergoes, the same amount of external force, or rather any force, as I mentioned that okay, this extra violent thing. So this came from here only, this idea that okay, I want to throw this stone and I want to check that okay. So he want, again I'm using the terminologies such as force and all, so that you can understand. Again, this was not there, and Aristotle had much more difficulty in figuring out. Now you might think that this is very obvious, but it was not at all during that time. So that why it took so much efforts, right? So he concluded that okay, the here the external force, basically the river force or the river flow, is slower, and here it is faster. So he concluded that okay, more force implies more motion. Of course, again that's a very vague statement, but more F implies more motion, more M, right? So that's what he told, that okay, if the force applied is larger, so the motion is also longer, or very to a large extent. So what he did, to conclude this, what he did, he took up a stone and he threw it with a great force, and it reached to some distance. And he picked up another stone and he threw it normally, and it reached another distance. So clearly the stone which it threw at a greater force reached covered much more distance than this stone. So he concluded that okay, more force implies more motion. Basically that means the extent of motion would be more if more amount of force is applied. Again, force, I mean more amount of, he called it something else, I am currently forgetting the term, but for us let's say it was the force, that okay, more amount of force is applied, that means more distance will be covered. So that was what he discovered during that time. And while in this process, of course, he was again doing the same experiments all over and again, because that was his task. He was very curious. So in this process, he also kind of figured out or did another another thing experiment that he also felt and would also look very logical to you, that why he did it. That okay, he saw that okay, fine. If I throw it in a slower, slower force, or rather slower extent, then it will cover a much more lesser distance. So what he tried was, he tried to, he, of course, he threw the stone in the direction of the river. So now he wanted to throw the stone in the direction opposite to the river, right? Because see, that's obvious. Because first time you want to check that okay, you throw it in the direction of the river, it takes this time. So what now? What will happen if I now throw it opposite to the direction of river? So he's just questioning himself. And of course, Aristotle, bhai sahab, what he does is that he takes up again stone, and he calls up another of his assistant, and he asks the assistant to do the same task. That okay, you stand here. The same river, it was the same fast river. Where you stand here, the same stone again. Here is his assistant, and here is Master Aristotle. Let me drop it here so that it looks like him. So Master Aristotle, he is standing, and he picks up a stone, and the river flows in this direction. And what he does is he throws the stone in opposite direction, right? So in the of the river flow, and then he asks the assistant to then he asks his assistant to calculate how much time it took. And now of course you can understand, then if the stone is thrown in this direction, it would take much more time, because the direction is much, or rather the velocity which we say is, on different direction. Now of course Aristotle did not know this. Again, this might look very obvious and very funny, but that was how it was discovered. So Aristotle, what he did, he picked up the stone and threw it to the direction opposite to the river. And he found out, his assistant found out that okay, it took much more time than in this case. And he did not do it for the slow river, because he knew that of course, even in fast river, if it's taking much more time, then of course in slower river, which was already slow, it would be much slower than this. So he here concludes that okay, if there is some resistance, or there is some opposing force, basically, then it will take much lesser amount of motion, right? It will undergo lesser extent of motion. So he similarly tried this also. He firstly he climbed up a hill, and he took a stone and he threw it down, and he saw that okay, it came down and it went down easily. And then another was there, that okay, in this building he picked up a stone and he threw it upwards, and now when it went upwards, he observed that okay, it was going upwards, and then again it came and it fell downwards. This was just observation, sheer observation. It came up, went up and came downwards. So he concluded that okay, in the upward direction, the the motion is less. Why the motion is less? Because, or the rather the extent is less, because maybe there is some resistive force. So of course he did not mathematically say that this what Newton did. What he told, that okay, the earth has a special attraction for objects like stone. That's why that stone is the attraction is towards. So the attraction of the earth is towards, basically earth loves this stone, right? So that's why the earth tries to pull it back. So hence there is the opposite or resistive force, and hence the motion of extent of motion is less. So that's why he also concluded another thing apart from this, that okay, more force implies more motion. He also concluded that okay, more resistance. Let me write R. More resistance implied lesser motion, lesser extent of motion. So if the resistance is more, again, this is very obvious for us, but it was not for him. I'm repeating it again and again. So before you just think that okay, I could have been also, I could also have been Aristotle. Of course you could have been, but the fundamental thing to question, you should have, right? So basically he just concluded there only okay, more resistance. So if the resisting force is more, so it will cover lesser extent of motion. The extent of motion would be lesser as compared to the, without, in the direction of force. So hence he reached that conclusion that okay, um, that this velocity, or rather the direction, the motion, amount of motion is kind of proportional. Of course proportion is a wrong word, he did not use it. He told that it depends on the amount of applied force. If the applied force is more, the extent of motion is more, and if the resistance is more, the extent of motion is less. And of course, as he was carrying out all these experiments in, in natural environment, so these were very well applicable. Very These observations held true, and this qualitative model aligned with everyday experience also, because people knew that okay, if we throw a stone upwards, we can ourselves see that it will come down. So that is why that model was persisted for very long time, around 2000 years I think it persisted. I'm not exactly sure, but it persisted many many years, because that was really before Newton. Almost that theory was also very much repeated, because exactly I hope you understand that it is able to explain all our observations, all our basically whatever observations we see. If we throw a stone, what we will be observed that okay, stone goes up and falls down. So he just made that observation and he kept record of that how it depends on force and resistance. Now of course, after all this, he was very much celebrated also, that okay, he can explain why all these things happen. So of course, the question came that why exactly this force and all this exist, like how, why exactly this resistance exists, and why exactly the force is attractive only, it's going down. And this question even Newton could not explain. Newton gave more mathematical terms. He just did the same thing. He just had the same observations, and he almost did the same thing. But what he did, he mathematized it, and of course using mathematical tools. So he was much ahead of Aristotle in that scenario. But he could not also explain that why did force act downward. It was not until Einstein that it was fully explainable, right? So again, it's really a long and very interesting story, but so I hope you are clear about it. That okay, that fine. This model was accepted. That okay, fine. It's good. It is explaining anything. But another hidden assumption, I hope you can see in that, in this framework or in this experiment or whatever that he proposed, his model, is that the rest in the natural state of objects. Right. So motion as such, we saw this motion, Aristotle, according to Aristotle, this motion can only be caused by some external force or some external resistance. It can be a resistance also. So any amount of motion requires some amount of force. But even but if the objects, they are at rest, so what about them? So their natural state is at rest. So why is not there again, why is there why there should be some internal purpose to go with the motion of the river and deposit a sand? So basically again, these were again failures, you can kind of say, because of course now as we know, we don't study it, because of course it failed. This model was later could not explain many things, and we found a better explanation, which we study up to grade 10th. So, critical assumption in Aristotle's framework is that the rest of the natural state of objects is that their motion is seen as something that must be sustained, right, by continuous force. So, without force, motion cannot exist. So, basically, that was, a kind of Aristotle's assumption, or rather, Aristotle's conclusion, you can say. He drew the conclusion from it. And of course, this was very well made theory, and this continued for a lot of time. But it, of course, we don't study it now. So I hope you by now you have uh, understood that it is very. It was rejected later, but a major cause for this rejection was the motion of the projectile, right? That even this building, and also let's say if I throw a stone and it falls somewhere, like I throw a stone and it falls something like this is again observation, it falls something like this. So he was asked that okay, fine, you are saying that this motion, it can only exist if a force is present, right? So he told that yes, you are right. But this posed a major challenge, is that during this projectile motion, there is apparently no force acting on this object. Let's say initially we throw it, let's say it reaches some point, and of course you told that motion is required to keep the object moving. But as you can see, it should have just come to rest. But why is it moving at all? Because here no force is acting, as we can see. So, of course, he was asked this question, and of course, he was trying to apply his theory everywhere, and he answered that he solved this, that okay, the surrounding air, the medium, uh, continues to push the object after it leaves the hand. So initially, the hand provided the necessary force, and when it left the hand, the medium, which is the air, it provided the necessary force, necessary, you can say, velocity, necessary force to for the motion to continue. So that was how Aristotle resolved it. Now of course it looks very intelligent, but later on as we come, because it is indeed a very intelligent theory, considering from where we came, from people of just having, yeah, from here, from just being born with a bunch of trees, you and your friends, we came here. So of course that's a very big jump. So of course it was very great and very thoughtful of him, this model. So of course it got very much recognized, and it is world famous, but we are not taught yet, because but of course there are many things which we are not taught in school, so of course we can't rely on that again. So slowly this, however, this theory was not very consistent, because it fails to, it does not, it is just experiments, right? And physics, as we know, is to mathematize it. Like by that time, after a few years later, that mathematics become very popular. Popular in the sense that mathematics, everything needed to be rigorous. Now Aristotle gave the conclusions, it was all fair, the conclusions were correct in fact, but it was not mathematically understood. It was just experiment. It was just an experiment, an observation. But of course people will question that why only this observation is arising, why not something else. So they wanted the mathematical rigorous proof that okay, this is the truth. And this, of course, these observations were made in environments where there were multiple factors, like just friction, air resistance, and what if they were ignored? Like currently in our syllabus, our so-called JE syllabus, what we do is that we ignore them. But during when Aristotle carried out these experiments, there was some external force, there was some air and all this, which you know provided a force. But what if this was absent? Then would that mean that all bodies would just remain where they were? Like how would they then act if there were no external air or something like that, no medium as such? So of course Aristotle could not answer that, because he did not have any mathematical form. All he had was his experiments, and of course these experiments explained very much the normal life, basically qualitative everyday experience. It could explain the everyday experience, but when more people came, they began to question that there is this force, there is that force, but if that force is not present, then that what will happen? So of course they were not isolated. And this projectile motion also contradicts the theory, as I mentioned, because now of course Aristotle had to say something to save his name. So that's why he told that okay, air applies the force. Now how much truth in that, will come to it, but he told that, but he did not have any mathematical proof or mathematical result that okay, air works. So now one might ask that even in the case of river, the air should act. So why not the stone, moves down also? Why it just flows like this? So that's again Aristotle, many things that could not explain. Again, that's why we don't read it now. So, and also later when astronomy and all, and of course now after this we will keep this session up to this. But after I tell something after Aristotle, of course the next big person, our Jane Mane Galilei, GL. Let me write. Of course, I am not going to again fully write his full name. But if you want, but of course, we need to pay him some respect. Galilei. I don't know his title, but I don't know the spelling, so I don't want to respect him. So the very next big person, Galileo, he comes, and after that, he and of course his life was not, and of course before Galileo there was Copernicus. There were many people, but of course Copernicus, he also made similar observations like Galileo, but of course he was killed. So again, why killed? Again, historical, that popes and all. So again, just people's ego, anyways. But can you realize that this Galileo, he further, of course he studied astronomy, he studied celestial objects and celestial bodies. And basically what he observed, that they move continuously without any observable force. Like now here, uh, Aristotle said that okay, air is present, that's why the force is acting. But in space, by that time it was known that in space there was, previously it was called that okay, there was some kind of a material like ether, I think, that okay, that material is present, that's why that this works, this entire, that's why there is a force in that medium, that's why the planets revolve around this. But of course Galileo observed that no, many such observations, many such experiments were proven that okay, there is actually no mutual at all. So again, that did not align, that Aristotle's you can say Aristotelian physics did not align much with the Galileo's experimental evolution, because he 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 developed, he used this telescope, and he used this he basically he was much more deeply involved in mathematical studies rather than just simple observations, because in space there is very less observable forces, like it's almost non-existent to human eyes. So that's why Aristotelian physics could not explain it much. So that's why we will learn more about it in Galileo's experimental evolution, what he actually did. And after Galileo, then we have further our great Newton. So, but again, this was just the very beginning of how the physics actually started. So after this, Newton came and he did wonders. I think Newton we have to spend a lot of time with. Even Galileo we will also spend a lot of time, more than Aristotle, because Aristotle was more based on mathematical terms rather than actual physics. Sorry, it was more based on experiment rather than actual experimenting, actual values and all those. So, of course, then we'll learn about Galileo in the next video. But I hope you did enjoy it, this story. Please comment if you have enjoyed, and we'll continue the series. I hope it will benefit all the people to learn. I hope you are getting some interest, that it's not something that it came from out of the blue, right? Anyways, so that's it for this video. Thank you. See you later. Bye.